This is session 13.2, Analysis of Series RLC Circuits. The first figure we see here shows the relationship between capacitor and inductor, especially their reactance when frequency changes. So the yellow waveform shows the capacitive reactance, and then the blue waveform shows the inductive reactance. When frequency increases, the yellow waveform capacitive reactance decreases. And at the same time, when frequency increases, the inductive reactance, the blue waveform, increases. At certain frequency, they meet, which means they are same. And that particular frequency is called a series resonance. Now let's work on example 2. The purpose for this example is to show when frequency changes, mainly increases, and then the change of the total circuit's impedance and its phase angle. Let's work on part A when frequency is 1 kHz. Because the capacitance and also the inductance are given, where capacitance is 0.022 microfarad and the inductance is 100 millihenry, we can use the reactance formulas to find their reactance. So Xc is 1 over 2 pi Fc, plug in the numbers, 1 divided by 2 pi, 1 kilohertz, multiply 0.022 microfarad. Punch these numbers into the calculator, we get a capacitive reactance of 7.23 kiloohms. And I use the inductive reactance formula. XL is 2 pi FL, that equals to 2 pi 1 kilohertz multiply 100 millihenry, that equals to 628 ohms. Now let's find the X total of this RLC circuit. X total equals to the absolute value of the difference between the two reactants. So we can use XL subtract XC, or XC minus XL, they are same, because at the end we just take the positive number. So XL is 628 ohms, subtract XC, 7.23 kiloohms. And then the absolute value of that is 6.6 kiloohms. From there, let's find the impedance of the circuit. This is the same formula for RC or RL circuit. So we use square root R squared plus, so instead of using XC or XL, we use X total. So that is X total squared. Plug in the numbers, that's square root 3.3 kiloohms square and plus the 6.6 kiloohms square. Put these numbers into the calculator, we get 7.38 kiloohms. Now let's find the phase angle of this RLC circuit. Theta equals to inverse tangent X total divided by the resistance, R. And then X total is 6.6 kiloohms. Resistance is 3.3 kiloohms. The inverse tangent of them, the ratio of these numbers is 33.4 degrees. Now let's try part B when frequency is 3.5 kilohertz. And we just run the same procedure, same steps for getting the answers. They are all the same except different frequency. We use these reactance formulas to find the capacitive reactance and the inductive reactance. Xc is 1 over 2 pi Fc is 1 over 2 pi times current frequency 3.5 kilohertz times the same capacitance 0.022 microfarad, and that is 2.07 kiloohms. And for XL, we use 2 pi FL equals to 2 pi times 3.5 kilohertz multiply 100 millihenry, and that is 2.22 kiloohms. And now let's find the X total. X total is the absolute value of the difference between XL and XC, and then that is the absolute value 2.20 kilo ohms, subtract 2.07 kilo ohms, which is 130 ohms. Next, we can find the impedance. Impedance Z is square root R squared plus X total squared. Plug in these numbers. Square root 3.3 kilo ohms squared added to 130 ohms squared equal to 3.30 kilo ohms. For the phase angle, we use inverse tangent X total over R. That's inverse tangent 130 kilo ohms divided by 3.3 kilo ohms. Put these numbers into the calculator, we get 2.26 degrees. The last part of the example is frequency that's 5 kilohertz. First, we get Xc, that is 1.45 kilohertz. Same formula, just change frequency to be 5 kilohertz. And then we get XL, change the frequency to the current 5 kilohertz, and the same inductance, 100 millihenry, we get 3.14 kilo ohms. The X total is absolute value of the difference between XL and XC. So we use absolute value 3.14 kilo ohms, subtract 1.45 kilo ohms, and that is 1.69 kilo ohms. Let's find the impedance. We use square root R squared plus X total squared equals to square root, and then R squared is same number, same resistance, 3.3 kilo ohm squared plus, and then the X total is 1.69 kilo ohms and square it, and that equal to 3.71 kilo ohms. Now let's find the phase angle. Theta equal to inverse tangent X total over R. The new X total for 5 kilohertz is 1.69 kilo ohms divided by 3.3 kilo ohms. So the angle is 27.1 degrees. This is example 2. Now let's work on example 3. This circuit has a voltage source of a root mean square voltage of 10 volts, connects to 3 elements. Resistor 75 kilo ohms. The inductive reactance XL is 25 kilo ohms. And the capacitive reactance XC 60 kilo ohms. We need to find the voltage across every component. And then we need to draw a complete voltage phasor diagram. We also need to find the voltage across the inductor L and the capacitor C combined. First, let's find the total reactance, X total. This is the absolute value of XL minus XC. That is the absolute value, 25 kilo ohms, subtract 60 kilo ohms. This is 35 kilo ohms. And then we need to find the impedance Z. The Z equal to square root R squared plus X total squared equals to square root 75 kilo ohm squared plus the X total 35 kilo ohm squared. Put these numbers into the calculator, we get 82.8 kilo ohms. This is the impedance of this RLC circuit. Use Ohm's law, current equals to the total voltage divided by the total impedance, Vs over Z total, which is 10 volts over 82.8 kilo ohms, and we get 121 microamps. This is the current for every element, since these elements are in series. The current is constant in series circuit. So VR is I times R, which is 121 microamps times the resistance, 75 kilo ohms. Using calculator, we got 9.08 volts. For VL, that is I times XL, is 121 microamps times 25 kiloohms, which is 3.03 volts. And for VC, the voltage across the capacitor, it is I times XC, which is 121 microamps times 60 kiloohms. Using calculator, we have 7.26 volts. Now let's find the voltage across L and C combined. The voltage across inductor leads, and then the voltage across capacitor lags. So over here, we can use 7.26 volts subtracts 3.03 volts. We are not particularly interested in the sign because we are interested in knowing the difference and then the positive number of the difference. In other words, is the absolute value of the difference. So we just simply use the larger number, 7.26, subtract 3.03 volts, and then we get a 4.23 volts. This is the difference. This is the voltage across inductor and the capacitor. Is the absolute value of it. Now let's find the phase angle of the circuit. The phase angle theta is inverse tangent the total reactance divided by the resistance. So is the inverse tangent 35 kiloohms over 75 kiloohms. Using calculator, and we compute that is 25 degrees. We can see the XC, 60 kiloohms, greater than XL, which is barely 25 kiloohms. This is a capacitive circuit. The circuit is more influenced by capacitor than the inductor. The current leads the source voltage by 25 degrees.